Hi, everyone. I'm Guy. I'm a PhD student at Stanford, and I'll be telling you about some joint work with excellent collaborators. Caleb, who was a PhD student at Stanford at the time of this work, now has graduated and is in industry. Carmen, who is a PhD student at Stanford, and Liang, who is/was all of our advisors. Okay, and this work is titled Computational-Statistical Tradeoffs from NP-hardness. I want to start by defining, or for some of the audience, redefining what I mean by pack learning throughout this work. So in pack learning, there's an unknown concept class, C, we want to learn. And in this talk, we're interested in the distribution independent setting of pack learning. So what that means is we have an unknown distribution, D, unknown to the algorithm, and also an unknown function, which has the guarantee that it is within the concept class C, but we otherwise don't know what it is. And the learner gets IID samples from the distribution. Okay, so each sample is formed by first drawing a draw of D and then labeling it according to the unknown target function F. The learner's goal is to generate an accurate hypothesis. Throughout this talk, I'm just going to stick to 99% accuracy. And we measure accuracy by saying if we drew a fresh draw from the distribution, how likely would the hypothesis be to agree with that? A few remarks here. Throughout this talk, we're thinking only about binary classification. So F is outputting 0 or 1. And also, we are working in the improper setting of learning. So what that means is the hypothesis H can be anything. It doesn't have to be in the concept class C. In particular, since much of this talk is lower bounds, that allows the learner more power, and that makes our task a bit harder. Okay. And within pack learning, there's this beautiful fundamental theorem, which says that the sample complexity of this task is exactly characterized by the VC dimension, a natural combinatorial notion. Okay, and this has upper and lower bounds. I'm going to spend just like 1 minute on this theorem. I'm not going to go over the full proof, but I think it's helpful to see exactly like what goes into it. First, there's the easy direction, which is essentially straight from the definition of VC dimension. Like the definition of VC dimension has kind of an obvious obstruction to learning using less than VC dimension samples. So that obstruction gets us one direction. And then the harder direction is a beautiful theorem that says, roughly speaking, this is the only obstruction to learning. This is based on the VC and VC dimension, and then also foundational work of Blummer, Anfort, Hausler, and Ormuth that says if one takes VC dimension many samples, there is always a good learner. And I just want to say very quickly how this learner works, because it's going to lead into the main question of this work. And the way that learner works is it just finds any consistent hypothesis. Okay, so what this theorem shows is you take your roughly VC dimension many training samples, you find any concept, any function in C that fits that training sample, and that one will generalize. It will have good accuracy on fresh draws from the distribution, everything with high probability. Okay, so it's a very simple learner. The proof is a bit more work, but it's a beautiful theorem saying that VC dimension characterizes learning. That said, there is a way in which this theorem is not satisfactory, and that way has to do with time efficiency, right? This consistent hypothesis finder, at least a naive implementation of it, requires a loop over every function in the concept class. And typically, we think of these concept classes as having exponential size. So this is a very slow learner, even if it is very sample efficient. And indeed, in many settings, the best thing we know how to do is such a essentially naive brute force. So naturally, what if we also care about time efficiency? For this, the first thing I want to say is essentially an observation by Pitt and Valiant shortly after the invention of pack learning that says if P equals NP, essentially you can do whatever you want. RP equals NP is just the randomized version of P versus NP. I'm just going to call it P versus NP in this talk. So what Pitt and Valiant say is, for any reasonable concept class, this has some very mundane requirements, like your concept class can't encode the halting problem, that you can use the power of NP to efficiently implement this consistent hypothesis finder, and therefore have a time-efficient learner that only needs VC dimension many samples. Okay, now this is a really cool result in the sense that it's not that we believe P equals NP. Most people believe this is not the case, but it at least says that good luck proving that time and sample efficiency is not always possible, because in doing so, you'd have to rule out, you'd have to prove, essentially the most important question in theoretical computer science. Okay, so that's a beautiful result. But you can still ask, okay, but what evidence do we have that time and sample efficient learning is hard? And for this, actually, kind of straight in Valiant's first work, a theory of the learnable defining pack learning, and also for this version of the statement, you also use some results, some foundational crypto results. But essentially, this says if cryptography exists, then learning is not always possible. At least time efficiently learning is possible. And this observation slash result actually rules out something stronger than what Pitt and Valiant guarantee. Right? They rule out something weaker, so it's a stronger lower bound. What they show is actually under crypto assumptions, not only is it hard to time and sample efficiently learn, but actually, even if you give me many more samples in the VC dimension, I still won't be able to learn. Okay, so that's very useful information for learning theorists trying to figure out what problems are tractable and what is not. Okay, so what are we left with? We're left with under one assumption P versus NP, we can do everything we want. We can learn time and sample efficiently. Under a not matching assumption, we get quite a strong lower bound that time and sample efficient learning is hard. Even actually just time efficient learner, if I don't care about sample complexity, is hard. But a point I want to make is that these assumptions are actually quite far. And one way to justify this is by bringing up Impagliazzo's beautiful manuscript on 5 possible worlds in complexity theory. So 5 different ways computers could have power in the real world. And each of these possible 5 worlds has quite striking different implications for the power of algorithms on various tasks. And collectively, the 2 results I've mentioned only say, they only answer the status of learning in 3 of these 5 worlds. There's a full 2-world gap between the upper and lower bound. Okay, so our main result, or at least the first way I'm going to state it, is showing that in fact there is no gap, that if P is not equal to NP, then there is a concept class that is hard to time and sample efficiently learn. In our lower bound, it goes actually a bit beyond VC dimension. It doesn't say it's just hard to learn with VC dimension samples. There's a gap there. We'll see more about that later. So essentially what this does is it gives a way of characterizing, probably the most important problem in complexity, P versus NP, in terms of a very natural problem in learning, right? These 2 resources we care about most in learning, time and samples, can we simultaneously have learners that are efficient in both ways? Okay, that was kind of the first part of this talk where I give one way of casting our result. I now want to give a slightly different perspective on the same result. This will be from computational-statistical tradeoffs. And a lot of things here will look similar, but there is some slightly different motivation. So what these trade-offs are they are settings where, as the name suggests, time and sample complexity kind of compete with one another. You can either have a learner that is sample efficient or a learner that is time efficient, but not both. In order to prove such a trade-off, you need a concept class with kind of a very interesting behavior at different sample complexities. The fundamental theorem already says that with less than VC dimension samples, all bets are off. There's nothing you can do. Okay, so that's this red region. But then you want there to be a yellow region, where when you have a bit more than VC dimension many samples, learning is technically possible, but it's computationally intractable. It would take, say, exponential time. And then you move, as sample complexity gets larger, you move into a regime where suddenly learning actually becomes quite easy, and we have polynomial time learners. This has a kind of some interesting messages. In addition to this inherent tension between sample complexity and computational complexity, there's also a nice effect here where there's like a positive message in the picture. Because if you think about the transition from the yellow to green region, what it's saying is if I increase my sample complexity by, ideally just a little bit, I can have massive returns in computational complexity, right? I can take a learner that would have required exponential time all the way down to polynomial time or even, say, linear. So it allows for vastly more efficient learners with just a few more samples. Okay, so these trade-offs have been very well studied. I'm focusing on pack learning. So within that setting, the foundational work is by DGR in 2000, which say these trade-offs exist, also assuming cryptography is possible. I should say that there is a lot of work on these trade-offs. Throughout kind of all of statistics and a lot of multidimensional problems exhibit these trade-offs that aren't always just pack learning. There was a whole Simons program recently that was mostly studying these trade-offs. Okay, so this is a very well-studied phenomenon. Right now, essentially, all of these results are based on crypto assumptions or other average case assumptions, nothing by a worst case assumption like P versus NP. Okay, so our main result, kind of cast in the second light, is that these computational statistical trade-offs exist also assuming P not equal to NP. Okay, I'm going to say a little bit more about this result now. So we're going to construct a concept class with this behavior. So as the sample complexity increases, the runtime of the best learner goes down. And what I mean, like I'll kind of describe this in a little more detail. This concept class has VC dimension that's 1. So that means with a constant number of samples, I can learn. All right, so that's this first upper bound 1. And we also show that the time complexity of doing that is 2 to the n, which is not hard to show in this particular setting. Then we show that if one assumes P not equal to NP, we get quite a strong lower bound on learning. The curve I've drawn here is the ETH version of that. It's where NP actually takes exponential time. If you gave other assumptions of P versus not NP, we'd have a similar curve. It would just look a little bit different under kind of different possibilities of how hard NP is. Okay, but if if NP takes exponential time, what we show is if you have even 0.1 n samples, vastly more than the constant factor statistically required to learn, you've essentially got no benefit, right? You still take exponential time. Okay, but then we show there's a sharp transition. As one moves from 0.1 n many samples to, say, 10 n many samples, suddenly the concept class is efficiently learnable. And indeed, it's actually in linear time learnable. Okay, so with just a constant increase in the sample complexity, from C1n to C2n, we have this vast exponential improvement in the runtime of the best possible learner. Okay, I want to put this result in a bit more context in terms of other related results you can prove about the hardness and easiness of learning. And for this, I want to compare 2 types of pictures one could have about a concept class. The first is what I've been talking about, a computational statistical trade-off, where there are 3 regions based on the sample complexity. First, it's impossible. Then it is technically doable, but will take a very long time. And then it's doable and efficient. One could contrast this to just an intractable learning problem, where there's only 2 regions, right? At less than VC dimension many samples, it's impossible. At more than that, it's possible, but it's intractable. And there's never a green region. So these later tasks always stay hard. And these 2 types of trade-offs these 2 types of intractability / trade-offs allows me to talk a bit more about prior work. So I want a 2 by 2 grid here. So one dimension is the type of behavior of the concept class. And these intractable learning problems, essentially, as soon as path learning was invented, we knew that some problems are intractable under cryptographic assumptions. And also we have under other average case assumptions. So like DLSS here is not a cryptographic, but a different average case complexity assumption that there are intractable problems. For computational statistical trade-offs, it took a little bit longer. Actually, this DGR work can be viewed as kind of a souping up of the Valiant observation. But nonetheless, we can still get these trade-offs based on cryptographic assumptions and also other average case assumptions. Okay, for NP-hardness, however, there is a barrier result. In 2008, Applebaum, Brock, and Shao showed that, roughly speaking, if you were able to prove that there was an intractable learning problem, if P not equal to NP, it would have some very shocking implications. It would be the polynomial hierarchy collapses or some of Impagliazzo's worlds collapse. You kind of rule out some of his 5 worlds. They do this for certain types of reduction. So it's not like a black box result. It depends on how the proof of NP-hardness is structured. So it doesn't fully rule out, proving this sort of intractable problem. But it provides evidence that it will be really, really hard to get something in this box. Okay. And then our result, gets NP-hardness for these computational statistical trade-offs. So there's kind of an interesting flipping here, right? Like for intractable problems, based on crypto, intractability seems much easier to prove. It happened earlier, and indeed the proofs are typically easier. But for NP-hardness, actually computational statistical trade-offs are quite a bit easier. Okay, so it's interesting observation. One thing that this requires is if we want to prove a result like this, and we want to evade this ABX barrier, which we do, we crucially need our concept class to eventually become easy. We need a lower bound that only holds at some sample complexity regimes. So I want to just spend like 2 minutes saying where that pops up in our reduction. So remember, our goal in our main result is to show that if one could learn this concept class in a time and sample efficient manner, then we get that one can solve SAT efficiently. And the way we do that is we set up our concept class to be for every possible SAT instance, we have a function that encodes the solution to the SAT instance. It like encodes if there's satisfiable if there is a way of satisfying it, what is the string that satisfies it. Okay, so this seems useful for solving NP problems. And then we want to implement our reduction. We assume we have a efficient learner using M samples, and so we now want to we now want reduction to give that learner a sample. And the first thing to do is we just draw unlabeled samples, x1 through xm. And at this point, we run into an issue, right? Our reduction does not know how to label the samples because it doesn't know how to solve SAT. So this seems like an issue. But here we crucially use that there aren't that many samples. So what our reduction does is it just says, oh, there are only m samples. That means there are at most 2 to the m possible labelings. So I'm just going to try them all, right? For each possible way of labeling this data set, it then passes it into the learner. One of those will be correctly labeled. So for one of those possible 2 to the m data sets, the learner will output a good hypothesis, which essentially encodes the solution to the SAT instance. And then the reduction just checks all these SAT instances. It checks all the possible solutions to find the one that satisfies the SAT instance. Okay, so this way of doing things really crucially relies on the fact that m is small to do this 2 to the m brute first sort of labelings. And this is expected because of this ABX barrier, right? We have to somehow have a reduction that really crucially depends on m and doesn't work when m is, say, n to the 10. And that's how our reduction avoids the barrier. Okay, that is all of the technical stuff I have time for. I now just want to recap our main result. So we showed that P versus NP can be characterized by 2 very natural questions in learning: whether every concept class is time and sample efficiently learnable, and also whether computational statistical trade-offs exist. Okay, so we get really nice characterizations of foundational questions and complexity in terms of foundational questions and learning. An open question is that this particular construction we use is a concept class that kind of encodes solution to SAT instances. It's not often the sort of things we're learning in the real world. And it'd be nice to have some notion of a more natural concept class for which we can base these computational statistical trade-offs based on NP-hardness. Okay, thank you for your time.